Hello students, welcome back. We completed up to section 5. Now let's go to section 6, factor group computation. Let's begin with some simple examples. Two simplest examples, almost trivially simple, g over e and g over g. Let's see, g over g looks like everything cancels out and we just get 1. And indeed, we are going to get a group of just one element, the trivial group. How about this? Basically, this is g over 1. So it should be g, and indeed, it's going to be the same as g. So that's what I claim. G over e is g, kind of like g over 1. And then g over g is this e, kind of like g over g is 1, if you consider the number of elements especially. Now, how do you prove it? Well, the tool we can use is right here, the fundamental homomorphism theorem. Let's begin with the homomorphism here, but as a matter of fact, it's going to be more convenient to consider an epimorphism, because you see, the target G prime can be too big, and all it does is just giving the algebraic operation, and everything takes place in a subgroup phi of g, as a matter of fact. So let's consider this. Phi is sending g to phi of g, and phi of g is actually a group as well because it's a subgroup of g prime. So disregarding this, we actually have an epimorphism. It's a homomorphism onto the image phi of g. So let me highlight this in purple and this one in blue. So domain is blue and the image is purple. Furthermore, let me highlight kernel in brown, and that's a structure. Domain over kernel is isomorphic to the image. Blue over brown is purple. This isomorphism is called canonical isomorphism or the natural isomorphism, but in any case, that's what you're looking for. An epimorphism, and then the domain of a kernel is the image. Okay, let's apply that over here. A certain map that starts from G, the domain, and ends at G itself, coming back to itself, onto itself rather, because this should be an epimorphism. You see, this is image, and its kernel is just E. So what kind of map is it? Element of G goes to element of G and covers entire G, and only E belongs to kernel, but kernel is the preimage of E, so only E goes to E. Well, there can be many maps, but one such map I can think of is the identity map. Everything stays itself, so it covers everything, and E stays at E, and that's the only one that's staying at E. How about the next one? This one is even simpler. This is a domain, and this is the image. In other words, everything goes to E. So it's a trivial map. In that case, everything belongs to the kernel. Indeed, here's the justification. We use the identity map, and there can be other maps too. For example, you can use inner automorphism or anything like that too, but identity map is just fine. And then for this one, we use the trivial map. In any case, the structure is the same. The domain over kernel is the image. Let's keep it open for a while. Now let's go to the next problem here. Recall that z over mz is zm, and then determine r over mr. Let's see, do you really recall this? Z over mz is zm. Let's see. Z is an abelian group, so every subgroup is normal, so you can consider factor group with respect to any subgroup. But then again, every subgroup is of this MZ form because Z is cyclic. Remember that? So every non-trivial proper subset, every non-trivial proper subgroup is of this form, MZ form, where M is positive. Yes, you can use negative if you want to, but why would you bother? The key is M should not be 0. And then we can consider the factor group, and that happens to be Zm, and that's the same as the old Zm we considered, because the normal equivalence relation that comes from the normal subgroup in this particular case is precisely the same as equivalence or congruence modulo M equivalence relation that we have been considering, well, all the way back from lesson 0 and even further. I mean, we have been spending so much time about this construction that I do not want to redo it. We spent already enormous amount of time already. So if you still have anything unclear about this, I'll just leave that to you. And I'll assume that you sufficiently reviewed it. And then let's go to this. R over MR. Do we get something similar? Here, the group operation is the addition in both cases. Okay, all right. R over MR. What does that look like? Is this significantly different from this? Well, think about that and give me an answer. Well, do you have an answer? Or did you already give up? Well, here we go. First, the non-singular case, when M is non-zero, you see, you're dividing by something, so M is 0 or non-zero is important. So non-zero, then you can easily divide. So you can always multiply by 1 over M, you see. Any real number can be written as M times another real number. And vice versa too, because we can always multiply 1 over M. Remember, M is non-zero in this case. So what do we have? We have R over R is 0, so we're in actually the second category there. Now the singular case, when M equals to 0, in that case, 0 times R is just 0. So what do we have? We have R over trivial, so it's R, so it's this one here. So here, from the first example here, 6.1a, second case, and the first case. So either trivial or the entirety. If you do the same thing with Q, yes, you're going to get the same thing because we use basically the multiplicative inverse idea, 1 over M. Okay, so much for B. Now let's go to part C. Determine Sn over An. Remember Sn? Sn is a symmetric group, the set of all permutations of n letters. And then An is the alternating group, the set of all even permutations. And then, of course, An is a subgroup of Sn. Remember all those? Please recall that every permutation can be decomposed as a finite product of transpositions, and that number of transpositions required for that product is not unique, but it is unique modulo 2. So whether it is even or odd is definitely determined. And then if you multiply two permutations, then the first permutation has, say, 500 transposition multiplied, and the second permutation has 3 permutations multiplied. Then add them all up, you get 503 permutations multiplied altogether. So you're basically adding up. If you add up, what do you get? Even plus even is even, odd plus odd is even plus odd or odd plus even is again odd. Remember all those? Consequently, we have to get something like this. Even permutation belongs to alternating group. And then if one is even and one is odd, even permutation already belong there. If both are odd, then odd permutation, another odd permutation. So multiply all the transposition from here to there, then you get odd plus odd, so even. So it comes back to even. So even permutations are already in there. Odd permutations, in that case, all odd permutations are equivalent modulo an according to this normal equivalence relation. Consequently, we can have only two cosets, an that covers all the odd permutations, and then a transposition times an, which covers all the odd permutation. Even permutations here, odd permutations there, just two elements. And that should be a factor group. So what do we have? We have Z2. Another way is a bit of a cheating, but you can simply count the number of elements there. The order is n factorial for symmetric group and half of that for alternating group, because even versus odd, there's one-to-one correspondence. So index is 2, so we have only 2 elements. It should be a group, so we have Z2. A bit of a cheating, but there you go. Okay, do we have enough time for... Okay, let's try that. Z4 times Z6 over this factor group. As a matter of fact, the kind of computation we want to do is this. Let's see. First coordinate is 0, and nothing comes from 0 except 0 itself. So this is, as a matter of fact, the same as Z1, because this is a trivial subgroup. And then let's see, this 1 generates entire Z6. So this is Z1 times Z6. That's what we end up with. So 0 generates the trivial subgroup, Z1. And then 1 generates everything, so entire C6. So this C6 and that C6 basically cancel each other out, and then what do you get? Z1 over Z4 over Z1. Well, that's the kind of computation we want to do, and we are going to justify that a bit down here. But for now, let's just do it hard way. Let's find out an epimorphism from the domain to the target. So that's the domain, and that's the target. And then the kernel should be this one. So that should be a kernel. So what kind of epimorphism can you think of? A homomorphism from blue onto purple, whose kernel is this? Well, let me show you the answer key. Here, just take the first coordinate, so projection to the first coordinate, and then there goes the kernel and image, and therefore the fundamental homomorphism theorem applies. The first coordinate has to be 0, and second can be anything, so 1 generates everything. That's how you get the kernel. It's simple. Once you get your map, then the kernel computation is simple. After all, we are dealing with cyclic groups, so everything is simple.